Hello everyone, my name is Alvaro, and in this video, I will be solving another problem from the blind Leetcode 75 problem list. Today, I will be doing problem 261, which is called Graph Valid Tree. So let's get to it. So this is what the problem statement says. You have a graph of n nodes labeled from 0 to n minus 1. You are given an integer n and a list of edges where edges sub I equals some a-b pair. And this pair indicates that there is an undirected edge between nodes A and B in the graph. Return true if the edges of the given graph make up a valid tree, and false otherwise. So we have this example right here. And in this example right here, we have a tree, right? As we can see pretty clearly. And the edges are 0, 1, 0, 2, 0, 3, and 1, 4. So the output is true. This, for example, is not a tree because there's a loop here, right? 1, 2, 3 is a loop that goes on infinitely. So the edges are represented by 0, 1, 1, 2, 2, 3, 1, 3, and 1, 4. And these are some of the constraints. AI does not equal BI. There are no self loops or repeated edges. Self loops essentially means that like you would have a node pointing towards itself. So like an edge 0, 0. So pretty much this constraint right here. If AI equals BI, then there is a self loop. All right. So if you haven't done this problem, now will be the time to stop the video and give it a try yourself because I'm going to explain how to solve it. All right. So I guess in order to find whether a graph is a valid tree or not, right, we need to understand what are the characteristics of every tree that make a graph a tree, that make a certain graph a tree, and how we can use those characteristics to distinguish those graphs with ones that are not trees. So the characteristics that I'm going to say are true among all trees, and this is something that you will probably learn in a graph theory class. At least this is where I learned it. Sometimes you might learn it in an algorithms class or something. I guess it just depends on the curriculum. But yes, so a tree. First of all, we need to understand that a tree is strongly connected. So strongly. And what does this mean? This means that from anywhere in the tree you can get to any other node. So here, right, from 0 you can get to any node in the tree. And from 2 you can get to any node in the tree by taking a path, right? From 2 you can get to 4 by simply doing 2, 0, 1, 4, something like that. In layman's terms, it essentially means that if you have this graph right here, there are no elements by itself. So no elements alone. Or components, because if you also had, for example, let's say a node that is a 5 and a 6 here that are connected with one another, but 5 and 6 are not connected to any of these, then the graph will still not be a tree. So you can go from one element to another, to any node to another, by taking a path. So that is one of the first characteristics. Now, what is the other one? The other one is that there are no cycles. So the graph is acyclic. So no cycles. If there's a cycle like in here, right? 1, 2, 3, then obviously it will not be a tree by definition. And now, what does the graph being strongly connected and having no cycles imply? Well, it implies that there will be a total of n minus 1 edges. And why is that? Well, so suppose that we construct, right, a tree with n nodes, and it has it's strongly connected. So for example, if we have, let's see, so it has n minus 1 edges, and this is going to be important for our solution. But the main idea here, right, is that suppose that you can have like more than n minus 1 edges or less than n minus 1 edges. So if it's less than n minus 1, it's actually pretty easy to see. But if we have n nodes, right, and we have n minus 2 edges, right, whenever we have an edge, we connect a node 1 with like a node A with a node B, right? So that consumes one edge. Then if we add another edge, then here we're connecting one node and one edge. So we're adding one at a time. So in the beginning we have two nodes and one edge. Then wherever we add the edge, assuming of course that there are no cycles, because if we added an edge from B to A, then we don't add any nodes. But first we start with, actually we can simply start with one node and 0 edges. So if we add an edge that is not a cycle, right, then we will be adding one node and one edge at a time. So in order to have n nodes at the end, we will have n minus 1 edges, right? Because we started with 1 and 0 edges. And whenever we add an edge to connect it with something, then we're adding one node as well. So at the end, we will have n nodes and n minus 1 edges. We'll never have n minus 2, because if we had n minus 2, then there will be a node like alone, or like, yeah, a node that's not connected. So what if we had more than n minus 1 edges? Well, at that point, right, all the nodes are connected with one another. Here we know that if there are n nodes and n minus 1 edges, all the nodes are connected with one another. No matter what edge we add, right, if we just keep the same number of nodes, if we add any edge, since all the nodes are connected in some way with one another, like you can get from one node to another, if we add an edge, we're going to add a cycle. But the graph, the tree has to be acyclical, so we can't add any more edges. Therefore, the number of edges that the tree is going to have will always be n minus 1. And this is going to be the fact that we're going to use for one of the facts that we're going to use for a solution, and also this. So now that we know these characteristics of a tree, how are we going to solve this problem? Well, one of the first checks that we can do is something really easy, and it's simply to see how many elements the edges list has. If there are no n minus, for example, if we have n, which is given to us, right? If n is equal to 5 and we don't have 4 edges, then we know by the definition of a tree that that graph is not a tree. So we must have n minus 1 edges in order to further check whether the graph is a tree or not. So that would be like the first check that we do. So if the length of edges is not equal to n minus 1, then we return false. So that's the first thing. Now, what do we have to do now, right? Well, what we have to do now is sort of like construct the graph itself and see whether the elements are strongly connected or not. The fact that the graph will be, if it is strongly connected and it has n minus 1 edges, then that means that there are no cycles as well. So we don't even need to check for the cycles. We could also check for the strongly connected component and whether the graph has cycles or not. And I encourage you to do that if you want to try that yourself, but I believe that that's a bit more complicated. So let's just get to check this and that. So what's next? So the idea here now will be to construct a graph. And you can use any sort of like representation that you want to, that you can use, but since we're given like all the edges here, I think like an adjacency list would be a good representation of the graph here. And the main idea here will be to simply process every single edge, right? So for example, we have n equals 5. So we're going to create 5 different entries, so 5 different empty lists in the beginning for the adjacency list representation. And whenever we encounter an edge, right, for example, 0, 1, what we have to do is in the entry for node 0, add 1 to the list of its neighbors, and in the entry for, in the entry for node 1, add it to the list of neighbors for node 1. So once we do that, we kind of have already the graph constructed. So let's get to work on that. So first, we can just create the adjacency list. And how many elements are we going to have? Well, we're going to have n elements, right? Because we want to have the neighbors for each node, and there are a total of n nodes. So here we can just simply use a list comprehension. So we can just call it adjacency list is equal to this. So we're gonna initialize each adjacency list as empty, right? And then we're gonna process the neighbors. So for I in range n. And after that, what we have to do is for now the edges is a list, right, of sublists. So it's a list of lists, and each list has 2 elements. So what we can pick is just simply node 1 and node 2 in edges. So each element in edges is a sublist of size 2. So node 1 will be the first element in that sublist, and node 2 will be the second element in that sublist. And the idea here is to simply just add each entry. So node 1, and then we just append it, node 2. So this means that officially now, node 2 is a neighbor of node 1. And then we do the opposite as well with node 2 and node 1. Like that. And this will take care of constructing the graph. So for example, for this example right here, right? Adjacency list sub 0 will look like this. It will have a 1, a 2, and a 3. Because these are all its neighbors. Adjacency list sub 2 will be simply this, because it's the only neighbor that it has. Adjacency list sub 1 will be 0 and 4, and so on and so on. I mean, for 4, it will just be 1, and for 3, it will just be 0. But you kind of get the idea of what we want to do. So now, we have constructed the graph, right? But when we want to, we have already checked that the graph has n minus 1 edges. But now what we want to check is whether the graph is strongly connected or not. So how are we going to do that? Well, the main idea here is to simply traverse the graph and ensure that all the nodes that we have visited, right, is equal to n. Meaning that what I said before, that whenever there's a node by itself, right? So if we start like at some point, if there's a node that you can't get to by any of, so suppose that there's like a 5 here lingering, right? A 5. If we perform a breadth first search or depth first search, doesn't matter really which one we do, starting at here, we will never get to 5. So the idea is to keep track of how many nodes we visit in the depth first search and the breadth first search. And if the number of nodes that we have visited on that search is equal to n, that means that the graph is strongly connected. Because if it's not connected, then that means that, we can't get to that node using the depth first search. So that's what we're going to do. Right now, what I'm going to do is just implement it iteratively, but what you can also do is just recursively if that's easier for you. But the main idea is that we're going to start from this node right here and just keep exploring all the other ones. So because we're not doing recursively, we're going to need to use some sort of like stack or, queue, whatever you want to use. If you want to do a depth first search or a breadth first search, it doesn't really matter. I'm gonna start with a depth first search, but you can do the other way if you prefer. It really does not matter. So the idea right now would be to simply keep track of all the elements that we have seen, right, in the graph, like we have done in other problems, for example, in number of islands. And that is to simply like not keep going over like the same edges back and forth all the time, right? And we're going to start it, we're going to initialize it with like the head or whatever we want to start with. I'm going to start with a 0, but it doesn't really matter. And then we're going to start with a stack. And the stack in Python can be like, just an empty list. Since like the list has enough features in Python, the array list, you can simply just pop elements in all one time. So that's good enough. And now what we're going to do essentially is the following. While the stack is not empty, right, we are going to grab the rightmost node, we're going to pop it, and after that, what we're going to do is we're going to loop it through its adjacency list, right? The adjacency list are the neighbors of that node. Now, if the node is a node that we have not seen before, so if it's not in scene, that means that we will need to process it. And what do we do whenever, and how do we process it? Well, simply all that we need to do is just append it to the stack so that we can repeat the same thing with the neighbors. And then we just add it to like our scene data structure. And that'll be pretty much it. And then at the end of that loop, we'll simply check if the number of elements that we've seen is equal to n. And if it's not, then we're pretty much done. So let's get to it. So while the length of the stack is not equal to 0, then the node that we want to process is equal to stack.pop. And now what do we do? Well, we need to check its neighbors. So for each neighbor in adjacency list to process, so right now we're grabbing the neighbors of this node. We have to check whether if it's not in scene, so if neighbor is not in scene, then we have to add it to scene. And after that, we have to append it to the stack to process it later. And this depth first search will just keep going and keep going until eventually you've processed every single node that you can get to from the beginning node, which in this case is 0, but you can start with any number. Ideally, I mean, you never know what n is going to be, so, as long as you start with a number that's less than n, you're probably going to be fine, because, the entries in adjacency list go from 0 to n minus 1. But yes, after that, you simply need to check whether the number of elements that you've seen is equal to n. If it's equal to n, then that means that it's strongly connected, because using a depth first search, we have been able to get from the beginning node to all the other nodes. But if the number of elements in scene is not equal to n, then that means that there is a node that we have not been able to get to using the depth first search. So that means that it's not strongly connected, because not all components are connected, because you can't get from all components. You cannot get from one node, from any node to another by taking a path. So simply all that we need to do now is, if the length of scene is equal to n, then we return true, else we return false. And I know I can return length of scene equals n. I'm just writing it this way so that, it might be easier to see for viewers. And this code should work. There you go. Eventually, like with enough tries, it beats like 90-something% of the solutions, or they're 80-something. But as usual, runtimes are a bit inconsistent, as you can see. But yeah, that's pretty much it. There you go, actually. Perfect. So now let's discuss the runtime and the space complexity of this algorithm. So for starters, right, let's think about the space-time complexity, or the runtime complexity, sorry. So right now, right, what we see here is some sort of loop and a loop inside another loop. So it might be a bit confusing to understand the time complexity, but let's think about it another way, right? In the worst case scenario, we are going to process every single node, right? And so every node is eventually going to be in the stack. So this loop right here goes into the stack. So that will be worst case scenario, big O of n. Now, this one right here, right, for neighbor and adjacency list, goes through all the edges for that node. But we have to think about this globally, right? How many neighbors in total are we going to visit? Like, how many edges are we going to find? Well, we know that this loop will only execute if there are n minus 1 edges, because we already checked for that, right? Because otherwise it's not a treat. So we will do a total of actually 2 times, because we've created like an edge from 0 to 1 and from 1 to 0. But the number of edges that we've created in the adjacency list is also it's also an order of n, right? Because it's dependent on the number of nodes that exist. It's always going to be n minus 1. So in total, we're going to process O of n nodes and 2 times n minus 1 edges, because there are n minus 1 edges, but we've created each edge twice, one for going from node A to B and going from node B to A. But yes, so therefore the total runtime of this while loop right here is still big O of n, because it would look something like n plus 2 times n minus 1, which at the end is like 3n minus 2, I believe, which is big O of n. And this node right here, this loop right here, similarly, this will only run if the length of edges is n minus 1, and that is proportional to n, which is big O of n as well. Therefore, the runtime of this algorithm is big O of n. And now, what is the space-time complexity of this algorithm? Well, similarly, we're going to be storing an adjacency list, and we're going to be storing a scene array and stack. But all the nodes, like the number of edges that we store, are proportional to n. So they're like big O of n as well. So the space-time complexity of this problem is also big O of n. I know this can be a bit confusing, so just let me write like a very brief explanation again. So the main idea is this. We will only run this part of the code and below if we know that the length of edges is n minus 1. Since we know at this point that edges has n minus 1 elements, edges has n minus 1 elements, the number of edges is in big O of n. Therefore, when we add the number of edges to the time complexity, so essentially we can say that, so therefore when we add the number of edges to time complexity, if it were to be something like this, right, like number of edges is n and the number of edges, we can call it e. E is writing big O of n, so it's the same as writing big O of n plus n, but this is also big O of n. So there you go. That's why it's big O of n both for space and time complexity. And that's pretty much it. Yep. I hope that the video was helpful. It's definitely one of those problems where like Leetcode starts to get a bit trickier. So something that I would not recommend for beginners, but for someone that has been practicing a little bit more and knows some graph theory and some properties of trees and graphs. And yeah, hope you enjoyed the video. Make sure you drop a like and see you in the next one. Bye-bye.